Okay, R1 and R2 are two parameters of a population growth model. If we look back to that last slide, these parameters are in there, right? R1 is going to be here, and R2 is going to be in the other species growth model. So it's possible that these parameters, if we change the values, could have an effect on whether the species coexist. But if we think back to the last video, we said that R1 and R2 actually don't have an effect on whether species coexist. Instead, they change the rate at which the population grows towards its carrying capacity. So if there's a low R, it grows slowly. If there's a high R, it grows very quickly. But it's the carrying capacity itself that's far more important than R. And so you can change R, and ironically, it doesn't have, or maybe surprisingly, it doesn't have any effect on whether two species coexist, only how quickly those species can grow when their populations are small. What actually has a much bigger effect is K, both K1 and K2, but also the competitive effects of the species on each other. That is, those competition coefficients that we called alpha and beta. Alpha now being the effects of species 2 on species 1, and beta here being the effect of species 1 on species 2. So we can think about coexistence in terms of meeting these two criteria. Is it true that the effect of species 2 on 1 is actually smaller than this ratio of carrying capacities? And you say, well, I don't understand why that should matter. Let's put some words on these values and think about it. And to do that first, let's rearrange them. Let's now, all I did, if you didn't follow what happened really quickly, is I'm going to take this K1 and bring it up to the top there. So I'm going to divide both sides, multiply both sides by K2, which is going to lead to this. Now, what are we saying here? We're saying alpha is the effect of species 2 on species 1. And K2 is the number of species 2 we might expect to see in the environment. So if we think about it, we're saying how many species 2 are we likely to have out there at the most? And what effect is each one going to have on me as a species 1, right? As an individual species 1? Multiply that together, that's telling you how bad competition is. And what it's saying is that value has to be less than your own species' ability to survive in that environment, or K1, the carrying capacity for your species. And so by putting words on these, we might say that the left side of that equation is how well species 2 affects or limits species 1, and the right side of that equation is just how species 1 limits itself. Because if the carrying capacity is really, really large, then what it's saying is there's a lot of resources for species 1 in that environment, and it's not competing with itself very much. But if the carrying capacity here is very small, it's saying species 1 is doing a pretty good job of limiting itself because there's a very low carrying capacity, which reflects very limited resources in the environment. And so these are the requirements. It just not has to be true that this is the case, but also, since we're talking about both species 1 and species 2 existing together, it has to be true that species 2 isn't being limited too much by species 1. Now, if both of these things are true for a population, then we can expect that indefinitely both species will be able to be found in that environment. That the populations will reach some sort of stable carrying capacity for both species. It's going to be less than those sizes of populations would be if they were alone, of course, kind of back to the Daphne experiment from the last video where we saw, when the Daphne were alone, they maybe reached 100-some individuals, but when they were with another species, they might have only reached 80 individuals. But still, you would find some individuals of each species. And that's what we mean by coexistence. All right? Now, let's actually look at some real data, because all of this is theoretical. And really, all this up till now has been reviewed to make sure that you have the right mindset to think about these data. Now, let's say we were to look at the actual parameters for populations of species. And in this case, this is the sort of thing that's very easy to do with single-celled microorganisms that you can grow up in the lab. Because you can replicate the populations easily when the population is just a flask or a test tube of these tiny little critters. And it's very easy to estimate the size of these populations. How would you estimate the size of them? Well, think about it. Would you use mark recapture? Probably not. Try to mark single-cell organism? I don't know what you would do to mark them. Better yet, what you can do is take a small amount of fluid out, like say a half a milliliter or a milliliter out of a jar, and then you could, under the microscope, count the number of cells. And that is sampling. That's what you're doing right there, is you're sampling the population. So it's like quadrat sampling, but in this case, you're sampling a volume of fluid. Now, if you do that, you can then estimate things like rates of population growth, little r. You can estimate the carrying capacity, that is the final population size when the population stops growing. And here's what you find for two species of single-celled organism. The first one of the genus Colpidium, so we'll call it Colpidium. The second one of the genus Paramecium, and we'll call it Paramecium. And you can see the bars here for black reflect Colpidium, and the gray bars reflect Paramecium, which is the legend up here. What I want to point out is that the per capita rate of growth of the populations, or little r, is dependent on temperature. And so for one species, it increases, and the other species, it decreases. So that's interesting. But is it important? Well, if you remember back to that last true-false question, we said r shouldn't have theoretically any effect on whether they both coexist, just how quickly the populations reach their carrying capacity. So let's just forget about that for a minute. We don't have to worry about that. Instead, let's focus on K. And this is the carrying capacity now of the two species. So for Colpidium, you see that the carrying capacity kind of looks like that. And for Paramecium, it's pretty flat. So we got this sort of like gradually decreasing line for Colpidium and a flat line for Paramecium. Now, what does that tell us about the potential for these species to coexist at these different temperatures? Because what we're saying is if we make it warmer, we actually decrease the number of Colpidium the population can hold. If we make it warmer, we don't change the number of Paramecium that this population can hold. That is, the resources that can permit Paramecium to live don't seem to change with temperature. And that's an important observation because what it tells us is something about what happens to this competitive dynamic. It tells us that Paramecium isn't going to be negatively affected by an increase in temperature, but Colpidium is going to be negatively affected. Now, we can also look at one other parameter, and we know that this parameter is important, and that's the effect of competition, right? Or in this case, I'm showing you one of those competition coefficients, or alpha. This alpha is the effective competition of Colpidium on Paramecium. So it's how well Colpidium limits Paramecium, that is, how competitive it is. And remember, those values can scale between 0 and anything, right? So they could be 1 if Colpidium and Paramecium actually were like identical in their resource needs, but they could be greater than 1 if Colpidium was maybe a really big cell that required lots of resources. But actually here you see all these values are less than 0.6. So what it says is that there isn't complete overlap in the resources between Colpidium and Paramecium. And if we look at this, it's about 0.5. That would mean it takes 2 Colpidium to equal a Paramecium. That is, if you're a Paramecium and you see 2 Colpidium, they're just as bad for you as competitors as 1 Paramecium is, right? So thinking about it like that, what's important here is the effect that temperature has on this competitive interaction. Colpidium becomes more competitive as the temperature increases. So this is interesting because we can put these two things together, and actually they go in the opposite direction. We said that if we are concerned about the effect of Colpidium on Paramecium, we would want to know about Colpidium's carrying capacity, and we would want to know about its competitive impact. And we could see that while the carrying capacity goes down, the competitive effect, the alpha, goes up. And so this causes us to think about competition now in a complex way, because we have to ask ourselves, what is going to be the impact of Colpidium on Paramecium at different temperatures? And at what range of temperatures might we expect Paramecium to be able to coexist, even though there's Colpidium out there in the environment competing with it? So we could look at this side and we could say, okay, what if the carrying capacity for your competitor was high, but its effect on you was really small? Remember, on that left side of the equation, it's alpha times k. That's the total effect on you. Is the number of them there are that are competing with you, and the alpha of each one. On the other hand, what if we had not that many individuals, but each individual had a pretty large effect? Again, it'd be alpha times k that matters. So the theme here that's going is alpha times k2. That value has to be really small, less than k1, remember, for Paramecium to persist. So look at that. Let me write it out down here, where you can see it in one place. Look at that, and now think about where along that range of temperatures Paramecium will be most likely to persist. In other words, where along that range is alpha times k2 going to be the smallest? And where is it going to be the highest? All right, now with that in mind, try this true-false question. True or false, paramecium are most likely to persist at intermediate temperatures. Take a minute to think about that, and I'll in fact go back to the last slide. Paramecium are most likely to persist at intermediate temperatures. Is that true or false?